Today I'm going to show you how to use our hglm package to fit more than 2 random effects, so multiple random effects. And in my example, I'm going to fit a model with 2 random effects. And this is a question I got from some students and colleagues. They were asking me whether hglm is now capable of handling more than 1 random effects, not only 1. And I say yes, but they didn't know how to do that really. Well, first of all, in the first version of our package that published on the R journal, at that time we were not able to do this. But now on CRAN we have the latest version of hglm where this feature is implemented. So hglm has 2 types of inputs format. How to say? You can choose to input your data using formula. And call the package, or you can input your data using matrix, your design matrix. The latter case is particularly useful when you have correlated random effects, and it's sort of hglm package specific way of defining a model, which is very flexible and is different from other mixed model packages in R. So before I show the example, let me start R and load the package. Okay, if we go to the documentation of hglm, if you scroll down to the example, first of all, you see that we originally had this semiconductor example using hglm to fit a linear mixed model with with structured dispersion. And now we can do this using a new function called hglm2. But this is not the function I'm going to use today. hglm2 takes formula using this type of random effect definition. This is the same as LME4, if you know that, and LME, those popular R packages. So if users are more familiar with this type of input, you can use hglm2 instead. Then we have an example for 2 random effects. This is a simulated example. This is not the one I'm going to show today either, but in this one we have a good example to show you how the input format can be different. So if you use hglm2, you can define fixed effects, 2 random effects in this way when you have a vector. So if Z1, Z2 is a factor or a vector of values that you want to fit as random effects, you can do this way. This is a very traditional and classic way in R LME4 package, for instance, to define random effects. But alternatively, we can use this type of input. So we give design matrix X for the fixed effects, in this case like that. We have Y, response vector, and design matrix or instance matrix for multiple random effects. It's going to be a column binding of each of the random effects design matrix. And we have a huge matrix in this case. We have another term called rand_c, where it tells the program how many columns there are for each random effects. So we say, okay, for the first random effect Z1, we have 10 columns or levels of factors. The second one we have 5. Then it's split in the algorithm to fit multiple random effects. So this is the different ways of input which I want to introduce here first. Okay, then we have our particular example, which is slightly more complicated. To clarify it, I made this document. Hopefully it's clear. the model I'm going to fit is like that. The linear mixed model with fixed fat x beta, 2 random effects G and W and E. To explain using my data, it's going to be the flowering time of a plant called Arabidopsis. It's fitted with fixed effects, in this case nothing. It's going to be an intercept term here. And we have genetic effect, G, and that's defined as a correlated random effect using the genomic kinship. So individuals are genetically correlated according to this kinship matrix that I already calculated. We have W, in this case it's spatial correlation because those plants are sampled from different places of the world. And we have latitude, those information, and I constructed spatial correlation matrix already, using which this random effect is defined. So we have this case, 2 random effects with correlation structure and residual term. That's a linear mixed model with 2 random effects. The way to fit this in hglm is not to give those matrices directly. And if you see other videos, you see the trick we do in hglm in order to fit correlated random effects is to decompose the correlation structure and redefine the model. So the trick is that this model is actually equivalent to the following model, to this one. So this is a general form. Okay, we got fixed effects Z1 U1, the first random effect term, the second Z2 U2, and residual. And here we have non-correlated random effect. This is just normal random effects with identity matrix times variance components, like that. And why it is like that is because we define those Z1, Z2 that satisfies these equations. So this is sort of cross product or square. Z1 transpose is K, Z2 transpose is S. So if you look at the variance structure of Y, these two are the same. So the variance of Y is actually K sigma G square plus S sigma W square plus I sigma E square. Also for this model. That's why we can do that. Okay. My terminal window is transparent, so I'm gonna leave this document here. Hopefully it's going to be visible all through my tutorial. Okay, now we're going to feed this. First, we check the data in my working directory. The way I usually do is to call the system command because I'm using a Mac. If your Linux is the same, so system call ls, it lists the current working directory, which files are in it. We have these files. The one I'm going to use is this first one, Arabidopsis go.r data. So I'm going to load Arabidopsis go.r data. Okay, now in my working space, we have K, S, and phi. And the Y vector I'm going to use today as an example is the first phenotype or response vector in this data set. This phenotype object has 108 columns for 108 different responses, and I'm going to use the first one. So I define Y as the first column of phi. We have 197 individuals. Sorry, it should be the second one because we have indices at the first column. So yes, this is our response. We have missing values. So we're going to record indices of missing values in order to make the fitting easier. So we have index is the missing value index of Y, like that. And we're gonna create, if we go back to this slide or the document, we're going to create those design matrices for hglm, which satisfy this. And you can use Cholesky decomposition if your matrix is positively definite. You can use eigenvalue decomposition, that's going to be the same if it's a symmetric matrix. In this case, I'm going to use a pretty general thing, singular value decomposition, which is slightly more difficult to implement, but it's more stable. So SVD1, I'm going to decompose the genetic kinship matrix K. So SVD, okay, like that. It's pretty simple. SVD2, I'm going to decompose the spatial correlation matrix S. Now we have two singular value decompositions. Well, if you check what's in your results for each singular value decomposition, you have D, U, and V. If you're familiar with this mathematical computation, you know that the U and V are vectors drawn from the matrix. And if it's a symmetric matrix, it's going to be the same. So V is actually the same as U in this case because it's symmetric. And D is a vector of, you can say eigenvalues in this case. So in order to construct Z1 and Z2, I'm not going to explain why I do like that, but that's correct. It's easy to prove and to check. So it is to use SVD1, the U object, this matrix, multiplies a diagonal matrix, square root of all the eigenvalues here. It's going to be our Z1. And I promise you that Z1 transpose is going to be K. There might be slightly different in a very, very minor numerical level, but it's going to be correct. So, second one, Z2 for spatial correlation, second random effect term. It's going to be like that. And I promise you it's correct as Z1. Okay, now we have Z1, Z2, these two instance matrices. The job is almost done. We need to create a design matrix for fixed effects, and that's going to be a columns of ones because we only have intercept. So matrix with 1, number of rows is let's do it without missing values, right? Remove missing values, y 1, like that. Probably we should remove missing values for Z1, Z2 now in order to make it clearer. So Z1 is going to remove those missing rows or individuals. Remove the missing values for Z2 as well, like that. Okay, but then you should notice one way is to, we first remove missing values from the kinship and the correlation structure. Then we will end up with different columns of Z as I have here. If you look at the Z1 matrix, for instance, now, is that we have 166 observations after kicking out the missing values. But we still have 197 columns, which is because we decompose it to be a square matrix for all the individuals. But now we have to keep the remaining columns to make sure that the correlation structure for the remaining 166 individuals are correct. But this is fine. We just need to be aware of the number of columns because we are going to use that in our model fitting command. And this is the correct also for that too. Now we are going to fit the model. Let's call it M2. We call hglm matrix input format. Y is Y, remove the index of missing values. We already have X, we already have Z, column binding of both images is. Tell the command, the program, how many columns there are for each random effect. Rand C, we have 197 for the first, 197 for the second. And this is going to work. The package is not pretty fast. At least for this case, it's gonna be fast, I think. Okay, it's done. So, summary of this model fitting object. We have a long list. We have EQ estimation converged in 10 iterations, which is fast. If you go above, there's going to be a huge list of random effect estimates. Okay, so starting by the top, we have the model fitting command. That's what we called. We have mean model fitting. Here we have fixed effect estimate, standard error, t-value, and p-values. This is the overall mean of my response vector, actually. We have summary of random effects, a lot. This is the best linear unbiased prediction of random effects, or BLUP, if you know that, for both. In this case, we're not interested in that. We're looking at the dispersion model. We're trying to estimate the variance components. Because we have two random effects, now we have two dispersion parameters for the random effects. Yeah, probably even missed an S here, but okay. So we have huge variance component for the genetic correlation and something for the spatial correlation. Well, this is a pretty highly heritable trait, so I'm not surprised that we have a huge value here. Just to show you, it's like that. We have gonna have a vector of values. We have multiple random effects. Dispersion parameter estimate is gonna be a vector of more than one values. And we have dispersion model. It's actually a gamma GLM internally that feeds this to estimate those values. So random effect term 1 is called random 1, random 2, like that. We have standard error for that as well. Okay. What else? When you have multiple random effects, you can still do model checking. I've implemented this plot hglm function. You can directly plot. It's an S3 method on the object, so you can just plot any hglm objects. You're gonna end up with hglm specific model checking plots that I made. You do that. It's going to take a while to plot everything because we have a lot of stuff. Okay. Right. I start with, now this window becomes too small, but I can shrink it down. There's going to be 3 model checking pictures that's created. The first one is checking the mean model. Well, in this case, we only have mean model. That's the model checking plot for the entire model. We compare fitted values with studentized residuals and the absolute value as well to see whether residuals are reasonably distributed normally, or whether it's balanced or not. Is a Loeys fitting to see whether it's straight or not. This is a QQ plot for the residuals to see whether it's normal. Well, in this case, not very normal because we have sort of some point mass here and a histogram of studentized residuals. Well, what does studentized mean? You can check the property description of our paper and in some literature. It's just residuals standardized by the hat values. Okay, the second model checking plot gives you this. This plots the hat values for the observations and some deviance checking to see, well, which individuals are more influenced, or how does the model perform numerically when you feed the model. The third one is a whole bunch of gamma QQ plot with histograms. Well, when you have only one random effect, it's going to be a 2x2 block. It's going to check the deviance for the mean model, deviance for the gamma model for the random effects, dispersion parameter. Because now we have two random effects, it's going to be a 3x2 plots with the mean model deviances checking and two random effect deviance checking. Well, if you have 10 random effects, you're going to end up with a very, very long graph. It might look horrible, but I didn't think about it, but it works now for 2 at least. So yes, that's how you fit multiple random effects even with correlation structure in hglm. Thanks.